In the last video, we turned the AI Club textbook into a long stream of integers. Now the question is, how does the model actually learn from that stream? In this video, we'll cover three things. How that integer stream gets carved into training examples, what the model is actually being asked to predict at each step, and how those examples get grouped into batches for efficient training. A Colab notebook that implements this process is shared in the description. Welcome to Scovia, where we turn AI ideas into everyday intuition. Let's quickly recall where we left off. After tokenization, we have one long sequence of integers where every chapter, every sentence of the textbook is encoded end to end. Something that looks like this. That's our training data. But you can't just hand this whole river to the model and say learn. Models don't read entire datasets at once. They learn from small, digestible windows, one chunk at a time. So the next question is, how do you slice that stream into something the model can learn from? Before we talk about slicing, it helps to be precise about what we want the model to learn. A language model has one job. Given a sequence of tokens, predict what comes next. That's it. And here's the clever part, that one simple task of predicting the next token is surprisingly rich. To do it well, the model has to absorb grammar, facts, style, structure, and long range dependencies, all from the pressure of getting the next token right. So the training examples are not hand labeled by humans, they are generated automatically from the token stream itself. Every position in the stream is simultaneously an input context and a label. So, a way to think about it is that the data labels are automatically generated. The data labels itself. And here's how it works concretely. We define a parameter called block size, sometimes also called the context window. Block size is how many tokens the model gets to look at before making a prediction. Let's say the block size is 4 for this example. In TinyGPT, a typical block size might be 128 or 256. Now take a small slice of our token stream. From the 5 token slice, we extract one training example. So you notice what happened here? The target is just the input that's shifted one position to the right. At every position in the input, the model is asked, given everything you have seen so far, what comes next? One window of 4 tokens gives us 4 separate prediction tasks. The model learns from all of them simultaneously. So what we just described is one training example, one window from one position in this train. But training one example at a time is very slow. So instead, we sample many windows simultaneously and stack them into a batch. Batch size is the number of windows we process in parallel. In TinyGPT, a typical batch size might be 32 or 64. So if batch size is 32 and the block size is 128, each training step processes 32 independent windows where each of that is 128 tokens long, which means that your X, which is the features, is of shape 32 times 128, and Y, which is considered the label, also has the same shape, 32 times 128. So the model gets 32 times 128 next token predictions to learn from. from a single step. That's why batching matters. It's what makes training on large datasets practical at all. One more thing that happens before training starts is that we don't use the entire token stream for training. We reserve a small portion, which is typically around 10%, as a validation set. The training set is what the model learns from, and the validation set is what we use to check whether the model is generalizing or just memorizing. Think about it like this: training is like studying, and validation is the exam. If the performance on the exam is much worse than on the study material, then the model is overfitting. So it's learning the specific tokens in your training set rather than the patterns behind them. For TinyGPT, we split the stream early, where the first 90% is used for training and the last 10% is used as validation data. So both of these get sliced into windows and batches exactly the same way. The only difference is that the model never updates itself based on the validation. It just gets evaluated on it. Let's zoom out and watch one full training step happen. The model receives a batch of 32 windows where each is 128 tokens long, and for every position in every window, it tries to predict the next token. It checks those predictions against the targets it has in Y, and it uses what it got wrong to update itself and become a little bit better at the task with each iteration. Then it does it again and again and again, thousands of times. Each step is a different random batch, and each step is also a small improvement. The model learns entirely by practicing next token prediction on randomly sampled windows of text. It does this over and over until it gets good at it. How exactly the model makes those predictions and how it turns a batch of token IDs into something meaningful, that's what the next video is about. We'll open up the model itself and look at embeddings and attention. One thing that's worth clarifying is that the model does not read the training data in order, like flipping pages in a book. Windows are sampled randomly from the stream, and the windows in a batch are independent of each other. Window row 1 and window row 3 have no relationship. They just happen to be processed together for efficiency. The model never knows which place a window came from, or what came before it, or what's outside the window. It only sees what's inside its context window and nothing more. So here's the takeaway: the model doesn't train on the full token stream at once. It trains on small windows that are sampled randomly from that stream. And then each one is an input sequence paired with the target sequence shifted one token to the right. Block size controls how much context the model sees, and batch size controls how many examples it processes in parallel. Every next token prediction is a free label that is generated automatically from the data itself. And that's a self supervised structure. So there's no human labeler required, which is a big part of why language models can be trained on so much text. I hope this made batching feel a little less like tensor operation and more like a very efficient study routine. And in the next video, we'll open up the model itself and we'll talk about embeddings, attention, and how TinyGPT turns a batch of token IDs into predictions. Please subscribe to Scovia for more visual walkthroughs of how AI actually works. And as always, stay curious.